This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Schurger and Tony Prescott.
So this is Paul Schurger for the Convergent Science Network podcast, together with Tony Prescott. And today we're speaking with Aaron Schurger. Welcome, Aaron, to our podcast. You were speaking today in our BCBT summer school, and you very much delved into the physiology of and behavior of volition, right, of free will. So do you think we can say anything meaningful about free will at all from a sort of scientific perspective?
I think in theory it's possible to do so, but I'm not sure if we've said anything meaningful yet.
Okay. But now, free will is a complex concept, as you also indicated in your talk. So is that the construct, is that a natural category of a follow Ryle? Is that what we should be investigating? Is that the right starting point? Or would you rephrase it and use a concept like volition or decision making?
I tend to use the phrase conscious will. Because I think free will is something that if you take the hardcore definition of free will, which is some uncaused cause, that's not something you can really grapple with scientifically. But you can ask questions about the relationship between conscious events and actions, and ask if there's if there's any kind of causal relationship between those two.
But in some sense, then you first have to also grapple with the so-called hard problem, right? Because now you link it to conscious states, and so how do we access these conscious states in an independent way?
Yeah, that I think is a direction that we're going in. It's not something that anyone has done in the past for that very reason. But we do now have some very reliable correlates of conscious perception. And so we could potentially start looking at those as indicators of the presence of a conscious intention, and ask whether or not it has the right relationship with the subsequent action, or at least the neural activity that brings the action about.
It's clear you're very cautious right now in how you approach this, and I understand that.
It's a conceptual minefield. So
exactly, but still, you have to leave some of the mystery to have something to explain. So have you just scraped off too much now of the free will volition phenomenon?
Well, we scraped away. Maybe we scraped away the mystery about the meaning of this signature, the readiness potential, which we thought was a sign of a decision. And what we've shown is that this may not be the sign of a decision, right? It right. Might be the sign of a random process. And if we're using this phenomenon, this readiness potential, as a temporal marker against which to compare the time of other events, well, we may have been deceiving ourselves by interpreting it in that way, interpreting it as a decision.
But now we already raised that quite a bit, right? But because first, I don't want to be too flippant about it. You might still believe it is flippant, but you said, well, instead of free will, I want to speak of conscious will, right? But you left the notion will in there as a construct, right? Can we do anything with this construct will? What is, also from a physiological perspective, as a physiologist, is will a useful construct? Can we do anything with that?
Well, if it maps onto something like an intention or an urge, something, then yes, I think so. I use the word will in this context to be almost identical with an intention. So, which is you could say a mental state or a neural state that represents a commitment to some course of action.
And an urge is sort of in the way that I think people would think about it, is almost something which is unconscious. I felt an urge. I don't know where it came from, but something urged me to go to do this. So the origin of the urge.
The origin of the urge, I guess, is unconscious. But the urge itself is.
So there's an interesting question you could talk about, sort of unconscious will potentially as well.
Yeah, in fact, that's something. It's very interesting that you bring that up, because it's something that I was just recently debating with colleagues and with some philosophers who really like this idea of the concept of a unconscious intention. But my problem with it is, how would you know an unconscious intention if you saw one? I don't know.
Behavior, action, arousal.
Maybe.
Well, I think it speaks to the whole question of agency. The fact that we have an experience of being agents is why we have this idea of free will in the first place. If we did things without feeling we were making choices, we wouldn't need to have will. But will explains why we have a feeling of agency. So I guess, and that feeling of agency is both unconscious and there's a conscious version of it.
I think it's important, though, to distinguish agency from volition. I think we can distinguish between the two. I think we can say that agency is the doesn't have to be the feeling, but the knowledge that my action caused some effect in the world. Whereas volition is that my thought caused my action. My desire or my intention was responsible for bringing that action about.
Also, usually then this distinction between, let's say, secondary or primary, secondary desires, right? So you might have an urge, but you must actually desire to execute or follow up on that urge, right? So it's a multi-level process that you commit yourself to. And so an unconscious or a subconscious urge or desire would never be identified as such by the agent, because it just plays out underneath the radar. Right. So, yeah, you always require, by necessity, this idea of a secondary and a primary sort of level of urges or desires, right? And then what you also need is an agent that actually owns these desires. But then there's also what's called the reasonable responsiveness, right? So that you can then deliberate on that desire. So these are ingredients you would need to then lead up to volition. To volition,
right. Reasoned responsiveness is an important one. That's, I think, in the past has been largely neglected, but that now everyone is talking about, which I think it's quite fair. It's true that if we want to give something this label of volition, it should have this property of responding to reasons. This is right. This is only,
and of course, this is also your trajectory, right? Because you move also in the direction to link the study of volition more closely with decision making, which of course goes in the direction of deliberation and reasoning and so on. But the other ingredient you need is the ability to do otherwise, right? So if I act following my urge and desire, I must also be able to understand that I have alternatives. I could have done otherwise.
Right, I could have done otherwise. Yeah, this is
an important one as well.
Yeah, and one that's very important to from a philosophical point of view, but it's very difficult empirically to show that you could have done otherwise.
Absolutely.
Yeah.
But okay, so this is then okay. This conceptual environment of free will, which is indeed complex, a minefield, as you said. But it's now you cut through that with this a laser in some sense by really zooming in on a very specific physiological feature of voluntary action, which is this readiness potential that was discovered in the 60s. So why do you think the readiness potential as such is actually telling us something about free will?
Well, I don't think it is. I think that's the issue, really. I don't think it tells us anything about free will one way or another. I think it tells us something about how the motor system works, some potentially interesting things, but I don't think it's a temporal marker for a decision. It's a temporal marker for a commitment.
Because this would go back to these classical experiments on the Bereitschaft potential that then fed into the limit experiments, and you laid this out for us in quite some detail, the Kornhuber and Dickey 60s experiments.
Mm-hmm.
And the big mystery that then appeared with Libet was like, well, if I look at the neural signals or the neural correlates of decision making, and I compare that to people's ability to declare where they are in the decision making process in terms of making decisions or committing to executing the action, there's a delay, right? So the brain only knows what it's going to do before you know it, which is of course already implying a dualism, some sense, right? So are you saying it was a surprise that was no surprise?
Come again?
when you say it doesn't tell us much about mission,
right.
Why were people were tremendously impressed with his result, right?
With the original,
there have been many attempts to replicate it, and no one could actually. There have been successful replications of it, and it's very much accepted as a physiological feature of decision making.
Yeah, it replicates extremely well.
Yeah.
Exactly.
So in that sense, it's a physiological fact.
Yeah.
But then a huge amount of trees have been killed to produce the paper on which many words have been written now about what this means with respect to free will, because it's the idea, well, the brain knows what you're going to do before you know it, therefore, right, there's no free will. So where did that interpretation go wrong? Because, okay, you have many methodological concerns, right, we can look at. But in some sense, why were people so easily misled about this at the time?
Well, because it very reliably precedes self-initiated movement. And so I think the first and it may be sensible conclusion to come to is that this is the brain's way of getting ready to initiate a movement, of planning and preparation for movement. But of course, the kind of data that we use to get it there, it's all correlational. So you could say, well, we've made the simple mistake of confusing correlation for causation. It's a bit more than that, but it's that as well.
Right. But isn't there also a hidden prior in this whole debate at this stage, right? Before we delve into the physiology and then the methodology, that there's an implicit dualism in the interpretation. There is this whole idea like, oh, every action at any time scale has to be caused by a conscious state, has to be preceded, therefore, by a conscious state, which seems an arbitrary assumption.
Yeah, well, no, I think with the readiness potential, what people are saying is that every action, or at least every voluntary self-initiated action, has to be caused by this same preceding neural state, not necessarily conscious, right? So I think the conscious bit, you can separate that out. And in fact, and we intentionally evaded the topic of consciousness when we first started working with this, because we just wanted to ask, is this signature, this readiness potential, the cause of the movement? Does this represent the brain getting ready to move? And I think that's what we, if you want to say, debunked in a way.
But now, so here with the readiness potential, it's a slow buildup of activity that peaks just before you initiate the movement. It precedes your ability to declare where you are in a position in the decision-making process. So the first way you debunked that story is to say, well, there's no unitary process underlying this. In some sense, it's an artifact of just averaging many observations, right? Because the idea would be that if you have spontaneous fluctuations in the brain, and these spontaneous fluctuations are sort of slightly biased by some form of evidence, let's say perceptual evidence about a task or an internally generated cue, then over many trials, this will go to some average state that will exactly look like what you call a readiness potential. But at heart, it is essentially just an integration of a highly noisy signal.
But even on single trials, it's the case. You don't really have to average trials to run into this problem. When you select a single trial based on the time of the movement itself, you've in a way selected a biased sample, right? Because that little piece of data that you're looking at ends with a movement. And if you want to understand how movement works, you also want to know what happens when there is no movement. So of course, in this case, because you have this biased sample, you see everything through the lens of, well, this is what happens before a movement. And you will, if you look at that, you'll recover in the average or on individual trials a tendency for there to be a ramping phenomenon, a ramp up to on the assumption that this is a threshold crossing type of phenomenon.
Right. And you also tested that hypothesis, right? By asking your subjects to respond as quickly as they could when you would cue the response, right? And then you would sort of link the cueing to where they would be in that integration process, right? So you would assume there's some decision threshold, and if they're further away from the decision threshold, you would predict if you now force somebody to respond, the reaction time should be longer than they are forced to respond when they're closer to this reaction threshold.
When they just happen to be closer, right?
Yeah, of course, yeah. And this is then just dependent on this sort of highly variable fluctuation.
Right.
Spontaneous fluctuation whose source you don't know about. So with that, you came to this idea that you could explain the readiness potential and also the performance from the perspective of a so-called distribution model. Right? So I integrate this noisy signal. When it hits threshold, I'm going. It's highly variable. Averaging across trials gives me something that looks like this readiness potential. But then when you tested that on your subjects, you could show that your model that implements this kind of integration of a noisy fluctuation, when you compared that to the EEG signal you got from your subjects, that it gave you a similar kind of response, right? So you see that indeed, if you compare fast and slow response trials, right, you see that this integration process has reached a different level. Right? And there's some offset. That's a difference between these two traces that you extract.
Yeah, and importantly, there's a difference not just before the movement, but before the cue to make the movement. And so these interruptions are random. I don't even know when the interruptions were going to happen. Nobody, the computer only knows, right? So what you see as a difference in electrical potential preceding the cue can't possibly be a preparatory process, because you can't prepare for movement that you don't know you're going to make.
Right. That's an important insight, right, from this model, that indeed there is no preparation. But now if you compare the model to the actual physiology, there is indeed a difference in the offset. But in terms of the details of how the trace evolves, it's not identical. Right. So if you would really lay the traces on top of each other, I would do some sort of correlation measure. I would not get one.
Right. It's qualitative. The what the model gives you relative to the reality is qualitative.
Right. So for instance, the model gives a much stronger decay in the trace than you observe in your subjects. While for the fast trials, it seems very constant in the model, practically constant.
Yeah.
Right, the level. While in your subject, it is still sort of sloping down. There's some form of decay, right? So there are differences here. Now, this in itself is not a criticism, because the model doesn't have to be identical to what you measure. But when is a model good enough, right? So to what extent did you feel this model was good enough to explain that data?
Well, I think it was good enough because it made a novel prediction, and albeit qualitative, but it told us we should find a difference between fast and slow responses in this particular direction. And that we found. Now, the fact that it doesn't map on to the reality exactly, that leaves some more questions for us to grapple with in the next iteration of experiments.
But it also leaves the door open. And in some sense, in the discussion part of your talk, we also came to that. I could also say, well, maybe the model that explains the data could even be simpler. Maybe it doesn't need to be drift diffusion.
Right.
You gave an example.
I gave an example,
So,
yeah.
Another example, maybe I could have just an oscillator that can exist in 2 modes, right?
Mm-hmm.
And it's a high energy mode and a low energy mode. And this would then account for the difference between the 2 traces. And it completely depends on intrinsic property, and just flip it between the 2.
Right.
It would be a completely solipsistic model, but in terms of the physiology, I could also account for this difference in offset, right?
Right.
So why is drift diffusion? So drift diffusion is not the simplest model.
Well, you can go simpler. I mean, what you need, what I said after the talk when we were discussing this, what you need at a minimum is pink noise. How you get that pink noise, maybe you can just say, well, I don't care how I got it. It's just there. The drift diffusion model gives you a sort of principled way that's grounded in prior research that gives you this pink noise.
Right. But then, okay, so now we have an alternative explanation, right? Of the readiness potential. So how many studies have really confirmed, you think, in your mind, the model you propose?
There are 5 or 6 different studies have come out that support the theory in one way or another. Mm-hmm. So an important one was the 2014 study by Murakami with rats, who found a ramping-like activity in the premotor cortex of rats when they were doing a task where they could basically spontaneously stop waiting for a big reward and just go immediately get a small reward.
Mm-hmm. Right. Yeah. Okay. Yeah. You mentioned that result, but ramping activity as such, is that sufficient as a signature?
Well, it's okay. So I spoke very quickly. It was not just ramping activity, but it was ramping activity that consistently reached the same level just at the moment that the rat left the waiting station and went to get the reward. So at least it's very consistent with the idea of an accumulator, of the output of an accumulator, right? We would expect it to look just like that.
Okay.
I mean, you pointed to some interesting evidence from crayfish and rat as well that I guess suggests that this readiness potential is something that's just common to brains.
Yeah.
And therefore, probably if the crayfish is doing it, what we normally think of as conscious volition isn't going to be a factor.
Yeah. I would agree with you on that.
I mean, and you also talked about the idea that this experiment, actually there is a weak imperative, you said to me. So it's almost that if people are making a conscious choice, it's when they walk into the experiment and agree to do this task.
Exactly.
And the task is designed so that specifically you're asked to suspend volition and, wait for that urge to come.
Yeah.
So it's really a task that's weighted against having any conscious volition that we would normally think of as conscious volition, sort of choosing to buy a house or move country or something like these. These are conscious choices. Whereas deciding to lift your finger in this task or whatever it's really designed to remove anything but the most minimal of conscious choice.
Yeah, well, I think
so. I mean, to that extent, is it really that surprising? I mean, for you, the result isn't surprising, but I guess you thought though why had the scientific community become so obsessed with this result?
Yeah, well, I think it is just a matter of lifting your finger. It is a very simple act. I'm sorry, I lost my train of thought.
Well, I mean, people have pointed to Libet as evidence against conscious control. But if you're a defender of conscious control, you can just say this experiment isn't representative of what we mean by conscious will. It's it's the minimal amount of conscious will. So even if Lebet was right and you were wrong, this doesn't really tell us anything about conscious volitional actions.
Yeah, I would agree. I mean, you need a signature of a decision.
Yeah.
And then you need to know that the relationship between the time of that decision and the time of your conscious decision.
So,
and if that signature is not reliable or doesn't mean what you think it means, then you can't make those inferences.
So given that that's the case for the Lebet experiment isn't a useful experiment to doing this, and the readiness potential isn't a useful signal, what would be another way of getting at conscious volition that you could imagine experimentally that would be more powerful?
I think a more powerful way that I alluded to at the end of the talk is to use a closed loop by a feedback system, or if you want to call it a brain-computer interface, to drive some external signal directly from cortical activity. And then you can ask questions about what happens when the feedback from you might say an intention, if you will, comes far earlier than you expected it to, far earlier than your brain expected it to. And that can tell you some things about at least the conscious feeling of volition.
But still, it would then depend on reportability, no?
You'd have to give a report, yeah. Yeah, so it doesn't work in the context of a, say, no report paradigm. This doesn't work.
Right. But the other thing is that for you like this Murakami result, which is interesting. Okay, we see some integration to threshold. We see how nicely lined up before this sort of self-initiated action to move from one port in the task as a mouse to the feeding port or the reward port. Okay. But we look at premotor cortex, right? Well, usually also in this whole debate on volition, people point more to, let's say, medial frontal structures, SMA, so more advanced in this hierarchy, right? So is it another issue that we're getting a little bit, let's say, unclear, but also localization of these phenomena now?
No, I think the area of cortex that they were looking at in the rat, M2, I think is the rat homologue of the SMA.
Okay.
If I'm not mistaken.
Mm-hmm. All right. So we have a reinterpretation of the Libet experiment, right? And in some sense you're saying, well, it's less magical than it looks like. But still, there is some source of, let's say, spontaneous activity that comes from somewhere.
Mm-hmm.
So is the spontaneous activity then an echo of something that you might want to call volition, a subtle agent that is trying to manipulate this? Or are you really thinking about this noise that is floating around in neural circuits?
I think it's the latter. Okay. I think it's just noise. I think you need more than that to explain and to account for volition.
So then what are the properties of neural noise in these cortical circuits?
Well, one of the most important properties is that it's temporally autocorrelated. And that is key in order to give you the kind of result that it's temporally autocorrelated. Another way of saying it's pink. It's pink noise. It's not white noise.
So how much physiological evidence is there that there's pink noise in these parts of the brain?
I think there's noise in the brain and in behavior tends to be pink. In fact, I would turn that around and challenge you to find white noise anywhere in the brain.
Sure. No, I would go more to the other direction. I'm not a big believer in noise. For me, noise just means there's a source of variability that you haven't identified yet.
Yes.
Okay.
Yeah.
So this is more where I was going with that. So to say pink noise, I think just means, well, we lump a lot of things together, and it looks like pink noise, right? But the other means there's some dynamical state that evolves with the memory.
Mm-hmm.
Right? So as long as you have a dynamical system with some kind of memory,
right,
then okay,
stickiness,
exactly. Then you have your big noise. Right? So in the way you decompose the readiness potential into, let's say, multiple highly variable traces, right? Maybe they themselves can again be decomposed in something more mechanistic that we can understand, that's more deterministic than pink noise itself, right?
Right.
Is that reasonable, or you think really there's really a pink noise source in the brain somewhere?
Oh, I see. No, I wouldn't say that there's a pink noise source in the brain somewhere, but it isn't. I think one of the interesting things about the model is that this kind of simple accumulator, its output has a 1/f power spectrum. It's pink, and that as I mentioned before, that helps to sort of ground it in some neurophysiology that has been well characterized in perception research, in decision-making research in general. So we have an instance where a very different kind of decision, a decision that is not made on the basis of a stimulus, at least not one that you have right there at hand, is governed maybe by the same kind of mechanism that all decisions are.
Right.
The brain didn't have to reinvent the wheel for this kind of decision.
So now we have a reinterpretation of the readiness potential. In some sense, you've deconstructed a notion of volition, and said, well, we can just think about it in the same way we think about decision making, and it doesn't really matter whether you want to call it volition or not. It's a decision making process that we're looking at.
Yeah.
And then there are more recent results, and you point, for instance, to this work by Fried, but also Soon and others, who then started to add more like a black box science to the whole story.
Mm-hmm.
So now we're going to say, okay, can I, as opposed to do a post-hoc analysis, I was going to say, can I predict, right, decisions given some classifier extracting features from my physiology? And I can do this in the Fried case on single cells.
Right.
And in the case of Soon, you can do that looking at fMRI.
Right.
So it was a bit of a game changer, right? It's this whole black box approach. And then surprisingly, these approaches seem to work. They could predict what the decision was going to be by the subject with some improved performance as compared to random. For Fried, it was 75% or something like this,
Mm-hmm.
right? And they could predict 500 milliseconds before the action was initiated what the subject would do. But for Soon, it was even more extreme. That's what Dylan Hines.
Right.
More extreme, that it could be up to 6 to 8 seconds or something like that. There's some extreme time window.
With fMRI, yeah.
And then the point was, okay, that almost seems to violate the basic principles of the universe, right? Because now I can look into the future.
Yeah, I mean, what I think would have violated the basic principles of the universe would be if you couldn't classify what someone was going to do based on prior brain activity. That would be strange, right? As if that decision just emerged out of ether.
But 8 seconds might be a bit long. That you can predict already before you even get the cue.
Yeah, well, I mean, let's say you're talking about a right or a left hand movement. I mean, it doesn't seem that unusual to me to think that several seconds beforehand, your brain might be in a state that will tend to bias it slightly towards one or the other. So I don't find that to be too hard to believe.
So also 8 seconds you would find not too hard to believe in the Soon experiments.
Yeah. I mean, no, I don't find it too hard to believe.
Okay. Okay, but that's interesting, right? Because with that you're saying that these fluctuations that would sort of bias you in one way or the other have really a rather long history in the dynamics of the brain.
Yeah, I guess that's what that points to, is that that if it is related to the phenomenon of autocorrelation,
mm-hmm.
so it's has a relatively sluggish time constant. Yeah.
But it's interesting because that would also reduce the states that the system can then occupy.
Yeah, although bear in mind that you're classifying slightly better than chance.
Mm-hmm.
I forget exactly how we're 58 or 60% correct, where 50% is just a random guess.
Right.
Would be a very different story, I guess, if it was 80 or 90%
right.
correct.
So when you came across this Fried result with the single cells using the support vector machine, or Soon with this fMRI classifier, at the time were you shocked by that or surprised, or this was also already done for you within the realm of the expected?
When I saw Fried's result, I wasn't too surprised. I was already at that time. I was already working on. I was already doing this work, and had already come to a lot of these conclusions. When I saw the work of Soon, that was much earlier. That was in 2008, I think. Yeah, I was initially pretty blown away by that. And later, well, sort of revised my way of interpreting the results. Yeah,
right. Because in the last part of your talk, you focus very much on also the methodological challenges that you face with this kind of analysis, right? And you pointed out a number of caveats, like for instance, if you use a sliding time window to make your estimates, you better be very clear where you put the reference to estimate.
Yeah, you want to align your time axis to the leading edge of the window, not the middle, or God forbid the tail end of the window, right?
Sure.
Because you don't want your classifier to be able to peek into the very future that it's trying to predict.
Mm-hmm. Right, exactly.
That would be cheating.
Yeah, absolutely. And then, so also you'll also looked at setting up the right reference conditions, like look at conditions without movement and with movement, right? And you talked also about the role of the autocorrelation in the signals that we're analyzing. So, but all these caveats point to the fact that we're overestimating these time windows. That's if there's an error, the error is in an overestimation of a time window in which you can reliably predict.
You mean if I understand you correctly, you're saying we're overestimating how far back?
Yeah.
Mm-hmm. I'm not sure it means that.
Okay.
Because I think, for example, in the Soon study, they weren't really using a sliding window. They were just classifying at each TR, at each point in time before the movement.
No, but still, they would have an autocorrelation to then take care of.
Yes, although I believe they did one reanalysis of some of those data, trying to rule out the possibility that this was just driven by autocorrelation. And at least their conclusion was that it couldn't be entirely accounted for by autocorrelation. But that, of course, leaves open the possibility that it could partly be.
Right. But in your own analysis that you presented to also show the relevance of these adjustments of the analysis method, you showed that the whole shape of that you already described as a banana, the whole shape of this readiness potential starts to disappear, right? And at this transition point at which you can start to predict it looks much more discrete or very, very punctuated in time.
Yeah,
it's less gradual.
When you have properly controlled conditions, where, as I mentioned before, if you want to talk about predicting the onset of movement, you want to have data that include movements, and you want to also have data that don't include movements as a control, right? And ideally, you'd want to have these two and compare them. So this in a more recent experiment that we're now just working on getting published, we did just that. So we used an experimental paradigm where you end up with data epochs that either terminate with a movement or terminate without a movement, but are well matched in other respects. And when you apply a sliding window analysis using pattern classifier to that kind of data, you can't using a very powerful classifier. We couldn't tell apart movement from non-movement epochs until the very last moment, until basically the moment at which the movement was beginning. And it certainly was no fault of the classifier itself, because at and after the time of movement, the classifier was at nearly perfect performance. Yeah. So you couldn't say, that's just because your classifier isn't good enough. Well, it appears to be good enough.
Yeah, but in some sense, isn't the consequence of that the shape that we gave to the readiness potential, isn't it more an artifact of, let's say, insufficiently tuned methods than that it's really in the signal, that's really the signal of the brain itself? Like also your examples, if you have a corrected signal, so for instance, if you take out the autocorrelation effect, right, that suddenly the meaningful part of your signal starts to look very different. It
Yeah.
was much more, let's say, an S-shaped kind of response, a more compressed transition point than the traditional readiness potential. So haven't you with that sort of deconstructed the readiness potential as an artifact of insufficient methods?
I think you can say that. Yeah, I think you can call it an artifact. If you want an artifact of time locking, having at least a tendency to time lock to crests in an autocorrelated time series.
Right.
Yeah. And if you time lock to crests in an autocorrelated time series, you recover the autocorrelation function, which looks like a slow curve.
Right. Exactly. Yeah.
So you've talked about having the right kinds of controls. Patrick Haggard, who was here last year, gave a talk on a little bit experiment. I'm sure you know his work on this.
Absolutely.
Has developed some quite beautifully controlled paradigms for comparing volitional with stimulus-driven responses. I think he was using sort of random noise movement, and you had to say which direction the dots were going in.
Yeah.
And his study, I think, also made it a bit more sort of mattered whether or not what response you get, because there was actually a monetary reward. So there's a bit more of an incentive to do the right thing or to do the most rational thing. And his data suggested that in the case of volitional actions, you see a reduction in the amount of noise.
That's right. Yeah. You see a slow reduction in variability over time as you approach the movement.
So how what do you think of that result, and how would you interpret it?
Well, I would really interpret it in the same way. That is to say that signal that variability can vary in much the same way that the time series can vary in a autocorrelated fashion. So the same logic that gets you the readiness potential in the experiments I did could get you this, let's say, decrease in variability.
But why would it be different between the volitional and the instructed trials? So,
well, because in the volitional case, the precise time of the movement,
right,
tends to be biased slightly by.
So it depends on this underlying process,
right? Whereas the cued, in the case of an instructed movement, that's not the case. So that's one of the key aspects of this explanation, is that when the way I say it is that when the imperative to move is weak or absent, meaning when this precise moment at which you move is not dictated by some stimulus, then you have this question, okay, I'm going to move approximately now, right? And so here goes, I move. And you're left with this question of, well, why did I move just right then when I moved and not 200 milliseconds earlier or later, right? There is some freedom there to play with. And if the answer to that question is, well, there are spontaneous fluctuations in neural activity, and they bias the precise moment at which you move, then if that's the case, then you're guaranteed to recover a slow, gradual buildup.
But I don't really see how this answers Tony's challenge, because Tony's referring to the Peter Haggard claiming Patrick, sorry. Voluntary control, lower variability. Cued control, higher variability, right? So,
or no reduction in variability.
Yeah. Okay. Within cued control, then we can go back to the literal decision making, where you start to drive the integrators, right? And as soon as you start to add a drive to these integrators, you start to overcome the more spontaneous fluctuation. So you would expect to see lower variability there.
Mm-hmm.
Right? So I don't really see how your explanation.
Well, that's what you get. You get a decrease in variability.
No, it was the voluntary case that was lower variability. Right.
Right. Yeah.
But when I was making the example, if you go to the decision-making literature where everything is cued, right? Then also for your model, if I start to drive your model with an external input coming from an external cue, I would start to reduce variability.
Yeah, and you would abolish this early tail,
right?
readiness potential.
So okay, my claim, and this is why I'm confused now. If you take the Haggard challenge, you say, okay, what is it? Higher variability. No. What is it? Lower variability, acute higher variability. But if you take your standard drift diffusion model with some, let's say, noise, if I now start to get an external cues and additional input, I start to reduce the noise effect. Right? So isn't that then counterintuitive from this drift diffusion perspective?
It's true that it does pose a bit of a challenge. But I think it's not, I think the case is not at all closed by that evidence, because again, that variability could itself be fluctuating in a random way.
Okay, but maybe a bit of a cop-out, no?
Well, and essentially, I mean, that's I would say, to be fair, that's one of the, if you want, one of the weaknesses of the model or of the explanation is that you can always keep saying, well, that could also vary, right? That could also fluctuate spontaneously. So if somebody comes up with a new phenomenon,
we just have another free parameter, right? And now we have the fluctuation we need.
Yeah. We said, well, that could fluctuate as well.
But maybe another response could be, also to the Tony's challenge, and some that people always ignore that the agent itself is represented, is sending a signal to a decision-making stage, right? So when you can imagine that the parietal areas, right, around the temporal junction that are implicated in states of self and agency are generating internal cues, right?
Right.
So
right.
in some sense, so the argument would then be internal cues have a higher gain, let's say, than externally generated cues. And then that way I might account for it. But that's not what you said.
But I think Patrick's result doesn't imply necessarily that that's due to conscious will, as you said. It could be due to some other internal attentional process.
He's agnostic. Patrick will be agnostic about that.
Yeah.
Mm-hmm. So it doesn't necessarily help the people who want to claim a role for conscious volition, which I think Patrick is one of those. So it could be some other unconscious process that's happening. Maybe it's linked to attention in some way.
Is attention relevant here? Why? I don't know. Why do you bring up attention? It's very confusing.
Because you're in a task where you're having to make a decision. So you're focusing on, am I going to, in his task, interrupt this trial, go to the next trial? Well, that's something you're fixating on.
And also you're instructed, actually. You're instructed to...
Yeah, well, there's money involved. So you make more money if you make good choices.
Yeah,
so that would be a reason for being more focused, which might reduce your neural noise. So.
Okay, that's fair enough. No, but then... So now we're having a problem, right? Because we have many problems. But let's start with Aaron's problem first. And so, okay, great. We're doing fantastically well. Here's limit. Looked very confusing. Conscious will is an illusion. What's the causal relation between conscious states and action and so on, right? You resolve that conundrum by saying, well, you have misinterpreted your signal, right? Essentially, right?
Yeah. Well, what's the relation between the readiness potential and action? Yeah.
Sure.
Yeah.
So you have to look. You have over-interpreted an artifact.
Yeah.
Right. And you can reduce the whole thing into a very simple model where we just have spontaneous fluctuations that have a little memory, so they can add up to some decision threshold, right? And it brings it in the realm of the standard decision making.
Yeah, I mean, it accounts for the data in a parsimonious way.
Right. But then you start to get worried about all the methodologies involved, and also these crazy long-range predictions people can make about decisions up to 8 seconds before they happen, which led to all sort of further speculation, certainly in the popular press. And then you start to apply all sorts of methodological caveats to say, well, actually, the real signal might look very different from the readiness potential. The real signal looks much more like a rather constant baseline state that shows a very rapid transition to a sort of an up state shortly before the decision.
Yeah.
Correct. Right?
Yeah.
But with that, you invalidate your earlier drift diffusion model. That's now irrelevant.
Doesn't invalidate it, right? In fact, it the idea is that it confirms it. So you say two competing camps or two competing hypotheses are for an early decision, which is, might say, I mean, he's not here for us to ask him, but I would say, as Libet's view, the decision is early. The neural, what I call the neural decision, right? To contrast it with the conscious decision. This is an early decision, whereas our model says, well, no, the decision only happens, and the Murakami used the same model, or the same kind of model, essentially. The decision doesn't happen until the threshold is crossed, and that happens very late in the game, very close to the time of the movement. And so that if you were the upshot of that, one prediction that it makes is that if you compare movement to no movement, they should look very similar until the very last moment, until that threshold, if you will, has been crossed.
Right. So we started with sort of a very complex picture on free will, and now we end up with something relatively pragmatic, physiological, controllable, in some sense, right? We're in the decision-making domain. Yeah.
Yeah.
Is that where you want to be, or do you want to again jump out of that and go back to this fundamental question around conscious will, as you call it? Because and sometimes now it's out of the picture, right? It doesn't matter to you. Now we're looking at decision making about self-generated actions.
Yeah, I think we should stay firmly grounded in the world of decision making, and self-generated actions. And I think there's more that we can do with this model and models like it. I think even if ultimately the model is all wrong, I think just the idea of taking this kind of phenomenon and bringing it, let's say, down to earth and grounding it in a computational model was an important step. And we've already gone beyond with this same model. We've done something very simple, which is just to add a second threshold, slightly lower than the threshold for activating movement. Let's say that we say, well, this lower threshold represents sort of self-monitoring process, so that when we cross that lower threshold, some information is generated to the effect that, well, a movement is very likely to happen very soon because I'm very close to the threshold. And using that simple variant of the model, we were able to make and confirm some predictions about the conscious urge to move, what Libet called W time for the will. So on trials where the subject waited a longer time to produce a movement, the presumption is that the ramping signal was ramping not as steeply as in trials when the subject responded early. And so the delay between the crossing of those two thresholds would be longer. And that would tell us something about the relationship between subjects' W time, when they felt they had the urge to move, and the movement itself. And that prediction.
But that says something quite disturbing about our notion of free will, which what we have interpreted till now as my moment of choice, I decided to make a movement, turns out to be just some internal monitoring system reporting that a bit of my brain that I'm not aware of has passed the threshold, and I'm going to make a movement whether I urge it or not.
That's what it may be.
So it's really quite a frightening conclusion for people who would like to be in free will, because it shows that these feelings that we have about will could just be completely wrong. Because you would have a feeling that I've willed that, but it turns out you haven't. Something in your brain has happened and this has popped into consciousness, and you have interpreted that as well. If it's true for that event, it could be true for all sorts of other decisions you make in your life, that some bit of your brain made something happen and then it was reported up to consciousness.
Although I wouldn't say that it's you said that maybe that feeling was wrong. But I wouldn't say
the interpretation of it that we put on it is that we made a choice.
I see.
So mens rea doesn't hold that, right? in that model.
In that model, no, not very well. Yeah.
So that's an important point, because and it was also the feeling I was having, like you invited us to some big party with lots of booze and God knows what, and entertainment. But in the end, you open a door and it's an empty room, and there's no drinks, no snacks, no nothing.
Yeah.
There's no decision making.
Yeah.
So haven't you now actually thrown out the dancers with the bathwater because of the limitations of your methods?
I mean, the goal here was not to prove that free will exists, right? But was to shed some light on how this all
No, you
works.
shed some light on it by turning the light off.
Oh no, you turned the light on and the room was empty.
The room was empty. I think.
No, but the risk is he actually turned on the lights in another room. Right. We have shifted. We have shifted now somewhere else.
No, I think this is where we thought the party was. You put the lights on. There is no party. There's no will. There's just these things causing stuff to happen, and you heard about it.
Mm-hmm.
Yeah.
So I mean, what do we do?
But it
with
is
that
deeply
now?
dissatisfactory.
Well, only if you wanted to believe in conscious will.
Well, no,
because you believed that there was a party to go to.
That's right. I like parties, but the thing is, there are things like mens rea, and there are costs of failure, right? So, if we really believe with Wagner and his friends that conscious will is an illusion and or not operational, there's a huge cost associated with that, because we're dehumanizing ourselves and we're giving up the sense of responsibility for action. The cost of that is huge. And if you do that to protect relatively primitive scientific models and methods, then I think that's a very naive move. Because I do believe, given the cost of failure, we also have to critically question the models we use. And we already know drift diffusion is great when you do really boneheaded tasks as a macaque monkey for months on end. Great, we get drift diffusion. But as soon as I make the decision task just a little bit more complicated, drift diffusion is not predictive of anything. If you give a complex brain a stupid task, you get a stupid code. And the stupid code can be deciphered by boneheaded neuroscientists. But the thing is, if you give a complex brain a complex task, it uses complex codes. And that's where the beauty is, and that's where the scientific challenges are. So what I feel now, we're a bit on the slippery slope. Oh, my methods are not really helping me. Let's just rephrase the problem. Let's scrape away all the complexity, so at least I can hold on to the method that has given me tenure. That's not for you, okay? But it's social knowledge of the field, right?
Right.
So drift diffusion drives me mad, indeed, because I think it is distorting our understanding of decision making, and certainly of voluntary decision making.
I don't think you can just point to drift diffusion for this. I mean, it's just
this is just
all you need is for that noise to be auto-associated. Yeah, so that's all you need for this result to happen. And the problem for your version is that you want to have some role for that experience of making a choice. And this result shows that you can have an experience of making the choice without having made any choice in consciousness that matters. So that, I mean, there may be other situations in which you make a choice that matters, but in this situation, you have the qualia, you have the experience of making a choice, but no, we've shown that
I appreciate your attempt to mediate here, but I take offense in your summary. Because the point I was making earlier, Aaron is showing to us that pink noise doesn't do the job. Unless it's some really special case of it. Because he shows a much more S-shaped transition. Right? Where you don't have sort of gradual accumulation of anything. There's accumulation of nothing and then a very rapid switch.
Well, that's when we squeeze the pink noise out of the picture.
Exactly.
Right.
Yeah, but that will be the real ground truth of the decision-making signal.
Abrupt.
Right?
Yes. Yeah. Late and abrupt.
So it looks very different than this sort of autocorrelate. That autocorrelate signal is some background thing that happens, has nothing to do with the decision-making process.
Right.
Right. This is the consequence.
It's part and parcel of the decision-making process, but it's just that when we look at it through the lens of this event-locked averaging, we see it in that in that misleading way. Yeah.
But it's like a non-specific contributor.
Yeah.
It's not a decisive contributor.
Right.
Decision, right?
Right.
But I think would be, as scientists, we must also be willing to say, well, we don't know. We don't know, but it's more than decision making, because for the free will case, there is a layer of the ability to reflect upon the decision, to own the urges to act, to not only act, but to also I want to act.
Mm-hmm.
I own this urge to act, and I experience that, and I can declare it. And it also is ability to, and I could have done something else. But there are many requirements of which the decision-making process is one of the requirements, but it's not the whole story. It's only one of the necessary conditions. And there I think we should be careful. So yes, studying decision-making can be fantastically useful. Drift diffusion models can be a great tool to do that, but they're not the whole story. This is why I got a little excited. I feel like we have to be careful not to collapse the complexity of voluntary action into the more reduced view of decision-making, which is only a necessary condition.
I mean, I think what we could agree is that in this task, it's a very minimal task for any kind of volitional control. And I think what Aaron's done is produced the sort of the minimal model of that. And Occam's razor said, well, why should there be anything more if this random process that's autocorrelated is enough to explain the result? Then that's quite possibly all there is. The disturbing thing for you is that the qualia associated with it are like the qualia associated with other decisions. So I think the pressure is now on people who want to defend, sort of some strong role for consciousness and decision making, to find another paradigm where you can demonstrate that.
Mm-hmm.
Because
you mean where volition then comes in as a separate factor, or what?
Yes. Mm-hmm. Yeah. Well, or in this paradigm to show that it's more than just this minimal model. This, that there might be something else that's happening in those last few hundred milliseconds.
Right. Would you agree with that summary, Aaron?
Yeah, and I think one of the things that is to be recommended about this model is its simplicity. It's a very simple model, and it accounts for the data, and that reverses the burden of proof in a sense. Now to the other side, say, well, why would millions of years of evolution result in a human who lives one full second behind their own self-made decisions? Yeah,
that's another interview. But the thing is, we already know, as you know, Libet, he understood the consequence of his observation or the implications of his interpretation. So he said, well, maybe the free will acts in holding back the action, in interrupting the action, stopping the action.
Right.
And actually, it turns out, if you start to do tasks where you have stop signals, so like countermanding,
mm-hmm.
then drift diffusion models stop working. They're not predictive of anything. Okay. So you really have your counter example. Then as soon as you start to voluntarily withhold action because you get a stop signal,
mm-hmm.
right? Then just integration to threshold is not explanatory in any way of the performance of a macaque monkey.
But the other way to, recover your notion of human and of choice is to embrace the unconscious as a source as part of the self and a source of your decision making.
Oh, absolutely.
So, and if you do that, then none of this is a worry, because you just say, well,
yeah.
I'm not just my conscious process. I'm the whole of what my brain is doing in the context of the body. And that collective system is making sensible decisions.
Absolutely.
And some of them are being reported to consciousness. It shouldn't bother me if most of them aren't, as long as they're good decisions.
And as long as your conscious urge is a meaningful best guess on the part of your brain as to the decision that you made and the time that you made it.
And if consciousness is able to monitor that and say, well, hang on a minute, we made a poor choice there. Maybe there's a role for consciousness and fixing.
You guys would finally read my papers.
I know. I'm telling you what was in your papers.
Thank you.
Okay.
You know that I see consciousness and also volition act towards the future.
Mm-hmm.
And all real-time control, as the ones you manipulate as experiments, is all subconscious. And because it's catching up, because consciousness tries to reconfigure you for the future. So you will yourself into the future. And that's the big mistake people make. They think real-time control, because I never for a robot to control anything, they think real-time control is conscious. It cannot be. It has to be automated, quick, because that's your survival system. It has to act in real time, and anything can happen to you. But what you then do, you reassess, and that's why the monitoring also comes in. You have to reassess, you revalue, you extract norms from your environment, and you reconfigure your real-time control. So in the future, you can will yourself to be better, right? And then, so in that sense, indeed, this is
right.
I'm not scared by that.
We're converging on a common view.
That would be really scary. So Aaron, so now that we all agree and are humming along, and you promised to read all my papers, so you have been wading through this really difficult territory, this minefield of volition, and you're still standing, which is amazing. That's a real accomplishment. So you're a great scientist. So given that experience and these accomplishments, what is Aaron's law that we should follow to understand the brain?
Well, I think what we should start looking at, and what hasn't been the case in the past, is look at instances where conscious states might actually play a role in an upcoming decision. So I think that in the literature there's been maybe because it's easier to do, maybe because it's sexier, but there's been a bias toward finding examples of things that you can do without consciousness. And that leaves open the possibility that there are some things that you do need consciousness for, but we haven't been spending our time investigating those.
So how do you turn it into Aaron's law?
I don't know about a law.
Look, it has to be printed on a mug or something. Right? It's like 10 words. What's Aaron's law?
Aaron's law is some actions, some volitional actions might actually be conscious. Might actually have a conscious antecedent, let's say. So we've looked at a lot of examples of tasks where you consciousness seems not to be involved.
So Aaron's law is some consciousness might play a role sometime.
Yeah, sometimes, maybe rarely, but maybe sometimes, right?
All right. The other thing is, so we were in Paris recently for a Living Machines conference, which was fantastic. And Tony, who likes Paris now, so he wants to go back to Paris, and he will come visit you 4 years from now.
Great.
And he will come and check. He will come in a notebook and check whether you have actually falsified or confirmed the key hypothesis for your scientific program. So what's the key hypothesis you would like to see tested in that time frame? 4 years.
4 years.
Prediction, yeah. Or maybe by then the channel tunnel will be filled up with concrete. So maybe earlier, not 2 years.
Maybe 2 years, yeah.
Okay.
Earlier. I think what I'd like to see done is a test of whether or not, to the extent that this can be done, whether or not one can draw a causal arrow between conscious states and actions. Mm-hmm. And if we could get a handle on how to come up with a paradigm to test that, I think that would add sort of counterweight to the kind of research that's been done over the past decades.
But what's the specific prediction then from that?
I guess it's true. I didn't give you a prediction.
That's right.
Yeah.
So I paid enough attention.
Okay. So yeah. So okay. A big prediction is this. You can what the model. One of the things that the model says is that the let's say the character of the noise will in part determine the shape of the readiness potential. So if you let's start with describing the power spectrum of pink noise has this 1/f slope to it. So that the slope of the power spectrum gives you what you could call the character of the noise, or the degree of autocorrelation in the noise. So one prediction that follows from that, highly counterintuitive prediction, or at least novel prediction, is that the character of the noise, the 1 over f exponent of the noise, should predict at an individual subject level the shape of the readiness potential.
But isn't it a retrodiction? Don't you already know that, given the results you have?
No, not at all. So that's very much a prediction and a strong one.
Okay.
It's difficult to test, but it is testable.
All right, Tony, you wrote it down?
It's on record on tape.
Yeah.
So Aaron Schurger, thank you very much for this conversation.
Thank you for having me.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.